Crystalline solids exhibit both short-range and long-range order, as described by the unit cell, shown here, with side lengths A, B, and C. The electronic structure of solids is represented by what we call the band structure. Let's define a couple of things here. One is the vacuum energy. Right? The vacuum energy is if you take an electron and pull it out of a metal, once you get it beyond the vacuum energy, it's not bound to the metal anymore. The Fermi energy, EF down here, that is the maximum energy that electrons can have in an object, right? And a metal, the difference, or any other species, right? The difference between that Fermi energy, the highest energy level of the electrons, point at which they're no longer bound, the vacuum energy, the difference between those is known as the work function. Important thing about a metal is you fill up all the states to the Fermi level, right? In a metal, and above it, they're empty. And importantly for a metal, the conduction band meets the valence band, and there is no gap between them. The valence band is completely full. There are nice empty states in the conduction band that allow for electrons to be conducted, and therefore a metal is highly conductive, right? In an insulator, there's a big gap, that gap energy, e.g., there's a big gap between the valence band and the conduction band. The gap is so big that even thermal excitations can't get you into the conduction band, right? Because of that, electrons aren't conducted. An insulator does not conduct electricity well. So insulators over here with a large band gap. Now, a very important class of material is the semiconductor. The semiconductor has a small gap, a small band gap between the conduction band and the valence band. The valence band is pretty much full. The conduction band is pretty much empty, but thermal excitations can get you across that small gap, or importantly, for the semiconductor industry, for photovoltaics, for photocatalysis, also impurity atoms that we can put in there intentionally can also lead to a bit of population in the conduction band, or some holes, some empty spaces in the valence band. So we can control the conductivity of a semiconductor, not only by the temperature, but also by the impurity levels. And this is what makes integrated circuits possible. And lots of technologically important materials are semiconductors. Again, for the integrated circuits that are in computer chips, for photovoltaics that make solar cells, for photocatalysis that you could split water and things like that. All of those things depend on semiconductors and this interesting band structure of those materials. Crystalline solids also have well-defined geometries for their interfaces. And depending on which crystal face you expose when you make a solid, there are well-defined geometries for those surfaces. This will be very important later on when we talk about heterogeneous catalysis, because different sites on the surface have different coordination numbers. You'll hear more about coordination numbers in inorganic chemistry. Now, the perfect surfaces that we get from ideal crystals, sometimes there are defects in those, steps or vacancies or add atoms, right? If you pull an atom out of here and put it on top, you get an add atom. And those different sites in the surface, whether different coordination numbers or defect sites, they all have very specific geometrical and electronic structure. The electronic structure can be very important for determining the catalytic properties of a material. And we'll talk about that again more when we get to heterogeneous catalysis. Now, as the size of materials gets small and you get into the nano regime, right? The structure of materials depends very much on the size and shape of a material. And the electronic structure also depends on the size and shape of particles in this nanoscale regime. When we get down to nanometer size particles, the properties of those particles are size dependent because of quantum mechanical and surface effects. This is a very important topic that we got to keep in mind. We can have very localized states on these nanoparticles that can, again, be very important for determining their chemistry. And so what we expect is not only our physical properties going to depend on the size and shape of nanoparticles, but when we get to particles that are in this nanometer size range, their chemistry is going to be dependent on their size. And in particular, their chemical reactivity, their catalytic ability may be different based on size.